Algebra 2, Lesson 35. Part A is about angles and polygons, and I have sketched out a few kind of random polygons here. We have a triangle, a quadrilateral, and a pentagon. And we're going to talk about, like I said, the angles. You know that the sum of the interior angles in any triangle is 180 degrees. I'm just going to write the sum of the angles right here. Okay, and if I need to know the sum of the interior angles of a quadrilateral, I could draw a diagonal, and this makes it into two triangles, and I know there are 180 degrees in this one and 180 degrees in that one. So the total of the interior angles in a quadrilateral has to be the sum of that, so 360. And likewise, we sometimes call this triangulating, so I'm making a bunch of triangles, and I'm always starting from one vertex. Okay, so I can make a pentagon into 3 triangles. They're each 180 degrees, like always. And so I can add those up, and then I know for a pentagon, the sum of the interior angles is 540. And you could keep on going. But it's really nice when we talk about polygons with many, many sides to not have to sketch one out and draw all those triangles. We can get a formula from this. Okay, so we see for each of these, this one had 3 sides, and it makes 1 triangle. Let's write sides, triangles. This had 4 sides, and it makes 2. This had 5 sides, and it makes 3 triangles. See, the number of triangles you can make is always just 2 less than the number of sides that there were. So what we're going to write down here, the sum of the measures of the interior angles of an n-sided polygon. So n is just the number of sides. The way we do that, we take the number of sides, subtract 2. All right, and that gives us the number of triangles that will make. But then we take that times 180 degrees because every one of those triangles has 180 degrees. So that is the formula for the sum of the measures of the interior angles of any polygon. All right, we'll be using that in just a little while. We're also going to talk about, I guess I'll go back up here. We're going to talk about exterior angles. Okay, the exterior angles, I changed my mind, I'm going to draw one down here. Okay, so we'll put it right here. I guess we have a pentagon again. When you extend a side beyond the polygon, so here's an exterior angle, and if I keep going around and just do that to one end of each of them. Sorry, I did this end. I'm going to go over here, that one, and this one, and this one, and then that one. 5-sided figure, there should be 5 exterior angles. Okay? Whenever I trace around the outside of any polygon, I'm actually making a circle, going around in a circle. So the sum of the exterior angles of any polygon is going to be 360 degrees. Okay, the sum of the measures of the exterior angles of absolutely any polygon is 360 degrees, because we go full circle. Okay, that one's one to memorize, and you have a formula for the interiors, which we'll be using right here in example 1. Okay, so here we have our polygon, and we're supposed to solve for x and y. So let's see. I know that all the way around the outside of this, the sum of all those exterior angles will equal 360 degrees. So that means 80 plus 40 plus 50 plus 65. And on your problem set, it'd be fine to just start adding those up immediately. In the notes, I want it all laid out so that when you're looking back, you know where the numbers came from. So it's all these, 80, 40, 50, 65 plus x plus 55, and I come back around. All those have to total 360 degrees. So then we can solve it. Okay, so here's 90 plus another 80 is 170, plus this is 235. I'm going to start writing these down. So we have 170, let's do this, plus those two is 120, plus 2x equals 360. I could have grabbed a calculator for this, but that wasn't too bad. Okay, so this is 290, and I'll subtract that from both sides. So 2x equals 70, which means x must equal 35. I don't need the degrees. Okay, we don't, x is 35. If I say it's 35 degrees, I guess that's degrees. What does that mean? It's just 35. Okay, we still need to find out what y equals. But now that I know x is 35, this angle is 35 plus 55 degrees. Okay, well that's 90, right? And these two angles make a straight angle, so y has to also be 90 so that they add up to 180. So I'm going to write x plus 55 plus y, those two angles, equal 180 because they form a straight angle. And so 35 plus 55 plus y equals 180. Therefore, y has to equal 90 when we subtract. So there's x. Sorry, it's a little bit off. Okay, and then there's y. That's it. We've done what they asked. We're going to move on now to part B. And in part B, we're dealing with quadrilaterals that are inscribed in circles. It means they're inside the circle and the vertices of the quadrilateral are on the circle. And I went ahead and already put some points on my circle. You're going to want to get those on there. And we're going to first remember that when you have an angle inscribed in a circle, the measure of it is half the measure of the intercepted arc. So if we happen to connect A and B, and also B and C, angle B here is inscribed in the circle, and the measure of angle B is half of arc ADC. This is the the intercepted arc. Okay, from that end of this chord to that end of that chord, that entire arc is the intercepted arc. So the measure of angle B is half the measure of arc ADC. Okay? If we also inscribe an angle here at point D and go from D to C and also D to A. Okay, now the measure of angle D is half the measure of its intercepted arc, and that goes from A to C on this side. Okay, so that's ABC. But you see that arc ABC plus arc ADC make an entire circle. Okay, here's the arc that goes with angle D, here's the arc that goes with angle B. They form the whole circle. So when we add the measures of those two angles, we're getting half of the whole circle, which means angle B and angle D added together have to equal 180, and it would work the same way for angle A and angle C. You have a quadrilateral inscribed in a circle. When that happens, the sum of the measures of any pair of opposite, not consecutive, but opposite, okay, B and D and A and C, is 180 degrees. And then we're going to use that for this next example, and that's supposed to be a circle with a quadrilateral in it. So you can sketch that out and label it like mine. It's similar to in the book, and they have an actual circle, so you might want to take a look at the book and copy theirs. And we're going to go ahead and use the things we know now to solve for x, y, and z. Okay. So, the thing we just wrote, opposite angles add up to 180. 80 and x are the opposite angles. So 80 plus x equals 180. So x is 100. And y and 75, that 75-degree angle, those are also opposite angles. So 75 plus y equals 180. So when you subtract, you see that y equals 105. And then we still need to find z. Z is an arc. Okay. We don't have an actual inscribed angle that intercepts that arc that's z degrees, but we do have this 80-degree angle going from here to here. So z plus 50 is twice of what 80 is. It's double that. So we could say that z plus 50 equals 160, because I'm going to write 2 times 80 so you know where it came from when you look back. Z plus 50 equals 160, and then we subtract 50 from both sides, and we get that z equals 110. We found x, y, and z. Here's x, here's y, here's z. Okay, now, part C, fractional exponents. Sometimes they're called rational exponents because the ratio is a fraction. All right, so here's an example with actual numbers to show you what this means over here on the right. The square root of 3 can also be written 3 to the 1/2 power. Okay, there's an understood 1 exponent right here on the 3. And when it's a square root, you're asking, what do you take times itself? 2 times, uses as a factor twice to get this number. So there's actually an understood 2 here. So what we do is the exponent over the index. If we had something like, 5, let's see, we'll do the cube root of 5 squared. That could also be written 5 to the 2/3. Okay, the main number is right here, and then the exponent now is this exponent over this index. That's that. So here it is, in very general terms, just using letters. X is the base. This is the nth root of x to the m power. And so it can be written this way, x to the m over n. M over n is the exponent. It's not some fraction you're multiplying by x. It is the exponent. And how you get this exponent is that exponent over that index. So we're going to do some of these. All right, in example 3 here, I see a negative exponent. I know I need to cross the line, the fraction bar, to change the sign of that exponent. So this is equivalent to 1 over 4 to the positive 1/2 power. Okay, to the 1/2 power is the same as square root. So that's the same as 1 over the square root of 4. The square root of 4 is 2, so this is a half. That's all there is to it. There's more. take a look at example 4. Okay, I have the negative exponent again. It doesn't affect this negative. Just negative will be in the front of my fraction. I'm going to cross the line to change the sign of this exponent. So I have 27 to the 1/3 power. And that's the same as the cube root of 27. So now I just need to know, what do I use as a factor 3 times and get 27? You can use a calculator. You shouldn't need a calculator. Also, if the directions ever say do not use a calculator, don't use a calculator. I'd like to see you doing these out. Plus, anytime they don't come out even, you won't be able to use a calculator. We'll just be simplifying the roots. But to demonstrate not using a calculator, I'm doing a factor tree. Okay, so I see that 3 times 3 times 3. So 3 uses the factor 3 times, gives me 27. So this is negative 1 over 3, negative 1/3. And that's that. Example 5. Okay, it's getting a little more interesting now. And we don't have a negative exponent, so we don't have to do that. This is 16s on the inside. Okay, now the bottom part is the index, so it's a square root. I don't have to write the 2. This will be the exponent. And I don't really want to cube 16 and then try to take the square root. I want to do the square root first if that's possible. So we're going to do it like that. The square root of 16, and why I said that, 16 to the 3/2 power can be written, this could be 16 to the 1/2 cubed, which is what I'm doing, or it could have been 16 cubed to the 1/2, because you know when you have a power raised to a power, you just multiply the exponents. Either one of these gives you 16 to the 3/2. I don't want to have to take 16 times 16 times 16 and then try to find the square root of that. Square root of 16 is much easier. That's 4. So now I have 4 cubed. So 4 times 4 times 4, 64. And that's it. Number 6. Okay, negative exponent again. So let's put the negative that's out there first. And then the rest of this, I cross the line to change the sign of the exponent. So now we have 8 to the positive 2/3. So I could square the 8 and then do the cube root, or I can do the cube root of 8 and then square what I get. And again, I usually find that to be easier, so that's how I'm going to do this. This is opposite of 1 over the cube root of 8, and then it gets squared. What do you take times itself 3 times to get 8? That would be 2. Negative 1 over, the stuff in parentheses is just 2. So 2 squared, that's 4. So I get negative 1 over 4. And that's the end. Have fun with all these polygons and circles and rational exponents.